Good morning. This one's going out by requests. There were some questions about this greenhouse gases and greenhouse effect activity. So, there are three questions here. What atmospheric gases are greenhouse gases? There's a typo too, sorry about that. What atmospheric gases are not, it should say greenhouse gases. And then finally, why are some greenhouse gases considered greenhouse gases? Why are some atmospheric gases considered greenhouse gases and others are not? So instead of like one question for this, we kind of have three all combined together. So I wouldn't stress that too hard as long as we answer all this stuff in some way. So before we get to the claim and the evidence and the reasoning part, I just want to point out a couple links. There was a reading assignment that you would spend a little time with. I would check that out first. And then there's this NASA website that talks about evidence, facts, and climate. I would check out all these links that are in here and read as much as I can, try and make sense out of it. There's a short little YouTube video here, about 8 minutes, where this kind gentleman talks you through some stuff that deals with the greenhouse effect. And then over here is this activity, this PhET lab simulation about molecules and light. So what I want to do is I want to focus on that one, and then I have a little simulation that I can show you about greenhouse gases and how that works. The first thing I wanted to do is talk about sunlight. So I got this graph. It is the light that comes off the sun. So if we, wavelength is down here, so we got high wavelength stuff and short wavelength stuff. This graph's nice too because it shows us the colors and how colors relate to energy, you know. So here's the visible light in these wavelengths, and that's what we can see with the eye. And then this would all be infrared, and eventually we'd get down here to like microwaves, which we can't see. We can only see that. And then over here we'd get into the UV, which is real high energy stuff, real short wavelength, and then eventually up into X-rays or whatnot. This graph's cool too because it shows me outside the atmosphere, like if you were in space, this kind of shadow looking graph would be the light that you would receive from the sun. This is like pure sunlight. But then down here at sea level, we can see that there's a huge difference in this graph. This is this this lighter section, or brighter sections down in here. This is the light that reaches the surface of the Earth. So we can see there's a huge difference between the light in space and then the light that you get after it goes through the entire atmosphere. So there's a significant amount of light of all kinds of different frequencies and energies that gets absorbed by the atmosphere. You can see these dips in here. These regions here are going to be real prominent drops. There's something going on here where something is absorbing this solar energy. Well, what is it? It's something in the atmosphere. Well, what's in the atmosphere? Well, it's gases. There's atmospheric gases. Well, let's take a look at those atmospheric gases. This is a graph of the light spectrum. It's kind of backwards from this graph. This graph has the blue stuff over here. The UV's here. But if I look at this graph, we got the UV over there. Same thing. But anyways, energy, right? So the blue stuff, the really short wavelength stuff is really high energy stuff, gamma rays, X-rays, or whatnot. And then if you look over here, the long wavelength stuff, right? Radio, microwave, infrared. This stuff here is low energy. And then right in there is that narrow little band we can see. So what gases are in the atmosphere? Well, we got this simulation over here, and this is how you're going to get your evidence. Question, claim, evidence, reasoning. Those questions about what gases are greenhouse gases. So how do we figure that out? Well, like this simulation's nice because I can shine light of different wavelengths on different gases. And right now I've selected nitrogen and I've selected visible. Well, why did I select nitrogen? Well, 80% of the Earth's atmosphere is nitrogen. Well, why did I select visible? Well, most of the light that gets to the Earth's surface is visible light. Most of the energy, most of the output of the sun, the energy of the sun is in visible light. So I can look at the effect on visible light on nitrogen, and the nitrogen's just kind of sitting there, right? The visible light doesn't do anything to the nitrogen. none of the energy of the light ends up in the nitrogen. Well, let's take a look at oxygen. Same thing with oxygen. So what I would say is, well, these gases don't absorb energy. At least they don't absorb energy from visible light, water, right? So they're not absorbing energy from visible light. Well, let me go back to nitrogen here, and let's check out the infrared. Well, okay. You know, there's a significant amount of energy here in the infrared coming off the sun, getting into the Earth's atmosphere. There's a huge absorption band right there too. Something's going on. Let's take a look. Oxygen. Oxygen doesn't get excited, just kind of sits there. Carbon dioxide. When infrared light hits a carbon dioxide molecule, that molecule gets excited. It just starts to wiggle around. It absorbs energy. And when it absorbs energy, it moves, it wiggles around, and it knocks into another CO2 molecule, and that one wiggles around, and that one absorbs energy. And they just start moving around more. The energy of the light turns into kinetic energy in the molecule, and that molecule starts moving around. And in physics and chemistry, when you talk about kinetic energy of molecules, that is temperature is used to measure the kinetic energy of molecules. So the temperature of the carbon dioxide is going to increase when ultraviolet light shines upon it. That makes carbon dioxide a greenhouse gas. It's a gas that can absorb energy. Check out some water. Water is too. Water wiggles around when you shine infrared light on it. Another one. So how do you like that? So what we can do, and what I want you guys to do, I won't do them all, but I want you to take a look at all these different types of light. Right? Most of the light coming off the sun is visible and infrared. Which of these gases are greenhouse gases? They are going to be the ones that wiggle around when you shine light on them. Ultraviolet, microwave, not so much, because they're not as important to this conversation as the visible light and the infrared light, because most of the output of the sun is in these frequencies. I'll put a link in the description to this one. Check this out. This is the Earth, the surface of the Earth. These red dots represent the material that the Earth is made out of. Right? Here's the atmosphere, yada, yada, yada. And I'm going to hit run here, and I'll show you what's going on. This is a graph of temperature, too. I'll put a link. You can change the brightness. Albedo, that's the amount of light that gets reflected. You can add clouds, I can add greenhouse gases, and we'll just hit run. So what's going to happen is this is visible light coming in, and I got this slowed down a little bit. This is infrared light. The ground is warm. Warm things give off infrared light. Infrared light is going up. Visible light's coming down from the sun. Most of the output of the sun is invisible light. So some things that can happen with the visible light, sometimes the visible light just gets reflected. Other times, the visible light is going to come down, and let's look to see if we can find one that, see, some visible light came down, and that visible light warmed up the surface of the Earth, right? So we got visible light coming down. It's warming up the surface of the Earth. Right? Sometimes the visible light gets reflected, but oftentimes the Earth gives off infrared light that reflects back out into space. This is a graph of temperature. Let me speed this up so we can watch this kind of run a little bit more quickly here. Check. Cruising right along. Here's this process. Now what I'm going to do is I'm going to add some greenhouse gases. Notice my temperature over here? It's actually kind of going down. Greenhouse gases, greenhouse gases. Right. Now I've got these molecules in here. These gas molecules, if they're a greenhouse gas, they are going to absorb infrared light, and they're going to get excited. And if I put more in here, I think I've got some computer bogging down issues. Okay, though. Wish this would go away. What's going on over here to our temperature? Seems to be going back up. seems to be rising at a rapid rate, even though that box is obscuring it. There we go. That's the end of our graph there. So, oh, it's really shooting up now. This is the greenhouse effect. And it's all due to these gases getting excited when you shine infrared light on them. So what you guys need to be doing is saying, okay, question, what are the greenhouse gases? Claim, you're going to list off which ones are the greenhouse gases. The evidence is going to be, what's going on here? Yes, it jiggles around. Carbon dioxide is a greenhouse gas. No, it doesn't. Nitrogen is not a greenhouse gas. And your reasoning is going to be, well, nitrogen's not a greenhouse gas because it doesn't absorb energy from infrared light or visible light. Carbon dioxide is a greenhouse gas. It doesn't absorb energy from visible light, but it sure does from infrared, etc., 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 for all these different gases. Let me show you one more. This is ozone, and this is ultraviolet. Interesting. Ozone, ultraviolet. Lucky for us, there is ozone in the upper atmosphere of the Earth, upper Earth's atmosphere. And what ozone does, there's a chemical reaction that takes place. The ozone will absorb ultraviolet light and break down in that process. So when that happens, when the ozone absorbs ultraviolet light and breaks down, right there, that ultraviolet light doesn't get to the surface of the Earth. And that's good because ultraviolet light is, see how it's all disappeared? You know, here's the outside of the atmosphere, ultraviolet light. The ozone is absorbing all of this ultraviolet light, which is good for us because that is really high energy stuff, and it's why we get sunburns. We don't get sunburns from visible light. We get it from the high energy ultraviolet light. There you have it. So listen, I hope that helped you guys out a little bit. Make sure you stay in touch. Subscribe to my YouTube channel and slap like. Anyways, have a good weekend. I miss you guys. We'll talk